Last time we discussed this example. Actually, we finished it, but I'd like to stress further on the concept that we learned. So we had a mass on this table revolving. This is mass M. And we had this rho. Then we have another mass M. So we denoted this distance by R, maybe this angle by theta, right?
Yep.
So 2 degrees of freedom, we wrote down the kinetic energy. I'm not going to rederive that. I believe it was mr dot squared plus 1/2 mr squared theta dot squared. And the potential was simply this guy, which is negative mg L minus R. Which means that your magic quantity, the Lagrangian, is T minus V. Here it is. Mg L minus R. And then we said, let's get the theta equation. You immediately realize that the partial L, the partial theta is 0, right? Your problem doesn't depend on theta. Not only that, also you have no non-conservative forces in the theta direction and no constraint forces in the theta direction. Actually, you don't have it at all. For the theta and R, non-conservative and constraint. So this, if you just simply apply the Lagrange's equation for theta, you immediately get that partial L, partial theta dot is constant. We call theta as an ignorable coordinate in this case, ignorable or cyclic. This is constant. And we're going to denote it as P theta. Why? Because it represents the momentum, the angular momentum, the corresponding momentum for the theta motion. So this guy, partial L, partial theta dot from here, from the green expression, you can immediately see that it's mr squared theta dot. So this is constant, and this constant is called P theta. Okay? This is what we did last time. We did all these steps last time. We don't need to rewrite. Now, the intuition says, well, if you want to get rid of theta at all, the theta coordinate at all, because there is no theta in your problem. You just have theta dot, and here is an expression for theta dot in terms of a constant and R. So the intuition says, well, what about having theta from here and going in this direction? Like I said, this direction is wrong. Okay? If you want to do that, if you want to get rid of theta and reduce your dynamics from 2 degrees of freedom to 1 degree of freedom, which is great because you can do great stuff on a single equation second order system, right? If you want to do that, then we define the Routhian to be your Lagrangian minus P theta theta dot. Okay? Now get this expression, please, for theta dot, and put it here and put it in your Lagrangian. The new R is void of theta dot. So the new R is void of theta dot, simply function of R and R dot only, and you can just copy it here. It's mr dot squared minus P theta squared over mr squared plus mg L minus R. And deal with this Routhian as if it's a Lagrangian in reduced number of degrees of freedom. So in particular, we wrote the Lagrange's equation for R coordinate, with large R being the Lagrangian, d by dt partial R dot minus partial R equals 0. And please, if you have any question, please stop me. Don't let it pass. This simply gives you mr double dot equals p theta squared over 2 mr cubed minus g over 2. No, there's no m. I already divided by m. Our dynamic equations of motion. Okay? Equation in one.
I think it should be n squared.
M squared?
Yeah, M
Yes,
squared.
that's right. Thank you. Any other question? So we got our double dot. This is what we exactly did last time. And the question is about equilibrium. The question is about equilibrium. So can we get an equilibrium? Which means, so p theta here represents the angular momentum. And because it's conserved, you can get its value from the initial condition. Give me my initial r and initial theta dot. I give you the initial p theta naught, but it's constant. It will remain unchanged. Okay? So if I start this from a certain r, say 10 centimeter, and I give it initial theta dot, this gives you immediately the initial p theta. Okay? And now I'm asking, okay, I give it some initial theta dot and some r. What do you expect will happen? I mean, this guy is pulling downward. It seems that this motion eventually should go all the way down, right? I mean, so we're asking, can we have an equilibrium? This is an equation for R dynamics only. Equilibrium means you have some constant value for R, right? This is equilibrium. Equilibrium means if you start at this R, you will remain indefinitely for this R, right? This is equilibrium. If you start there, you will remain indefinitely. Is there a magic value for R that if you start there, you will remain indefinitely? With R fixed, I mean, it doesn't seem intuitive, but here is your dynamics. How to get the equilibrium from here? How to get equilibrium from this equation? How to get equilibrium? R double dot equals
0.
R double dot equals 0 gives you the equilibrium. Solve this equation for R. You immediately get R equilibrium cube is what? Is P theta squared over M squared G, right? So, yeah, indeed there is a value for R. Indeed there is a value for R, a magic value for R corresponding to the initial momentum. Okay? So give me an initial momentum, I tell you the magic value for R that it will remain constant. Okay? So, this is an equilibrium, meaning that if you start right there, you will remain there indefinitely. But what about any small perturbation from that equilibrium? We imagine that, okay, I start at this magic R, whereas the initial angular momentum gives you sufficient angular velocity, inertial load in that direction, right, to balance the tension. And the tension here is balanced with the weight. So this is balanced. It's like a dynamic equilibrium. It's equilibrium, but in motion. That's fine. But now we're asking more. Okay, start right at this R, and I give it just punch. I'll push this mass downward. What do you think? I mean, it's supposed to, everything goes now downward. That's fine. We start at the right R, but you push it downward further. Why it ever will go back to its equilibrium? Why? So this question is a stability question, right? It's not this is equilibrium. Okay, you do have an equilibrium. I want to assess the stability, the tendency to go back to equilibrium upon disturbance, right? So it's always like this. The notion of equilibrium is different from stability. You might have an equilibrium, but this equilibrium per se may or may not be stable, for sure. You should be familiar with these concepts. How to study the stability of this guy, of this equilibrium? I told you some useful trick last time. If you have your acceleration's function of position, then please define this to be coming from effective potential. Because it's function of position only. If you have your forcing or acceleration function of position only, it seems to be coming from potential. It's an effective potential. that accounts for motion, not only the static potential that you have in the beginning. So I will do this definition, which means you can get your V effective by integrating this right-hand side and putting a negative sign. So this gives you what? This gives you P theta squared over 4m squared R4 plus G over 2R. This is your effective potential. And you can sketch it if you like. Last time we already did that, we sketched it. Your V effective versus R, we sketch it because it's easy, it is, so this is R squared, right? We integrate. Is it 4?
No, so it's
Yeah, 4, that's right. Okay, we sketched it because it's easy. It's 1 over R squared plus R, linear plus 1 over R squared. This was easy, so it was something like this. Okay? If you have the numbers, you can plot it using MATLAB, you can do whatever you like. It's not our objective now how to plot the function. In particular, the point where the first derivative is 0 is what? First derivative V effective by the R is this guy. When it's 0, gives you the equilibrium point. So this is R equilibrium, okay? So this is another means of getting your equilibrium, the value of equilibrium point. Plot your V effective versus R and get the points where the first derivative vanishes. When the first derivative vanishes, it may be minimum, it may be maximum, right? If the potential is minimum, then the equilibrium is stable, like we discussed last time. So immediately by looking at this curve, I can say that this equilibrium is stable, which means if you start anywhere, I don't care, start somewhere, okay? Give some initial theta dot. What will happen? This motion will go eventually to R equilibrium, and from that R equilibrium, if you push down, what will happen? It will come back. Interestingly, right? It doesn't seem intuitive. And we have many examples in nature where rotation and oscillation defy gravity. Okay? We have several examples. This is one of them. We have the inverted pendulum case. If you vibrate it up and down, you also defy gravity and your pendulum will not fall down. But the take-home message here is how to use the V effective thing. If you cannot sketch, this was easy to sketch. If you cannot sketch, how can I tell whether it's minimum or maximum? Anybody can remind us?
No, something that we might do is find all the
Take-
R's and
take
like,
double
plug it
derivative.
in V effective and see which is the minimum.
Yeah, how to check the minimum or maximum?
double derivative.
Double derivative, right? You need the V effective, double prime, and evaluate it at the value. This should be what? For
Negative.
minimum.
Positive.
Positive for minimum, right? This is the minimum shape, right? So it should be positive for stability. So the V effective should be indeed minimum, i.e. this guy is positive for stability. Any question about that? Any question, please? Any question? It's a nice trick, this V effective kind of thing. You get the effective potential. It's not your static potential, but the effective potential. Any question, please? Any question? Yes, please.
So if there are multiple values of R for which there can be multiple minimas and the global minima is equilibrium and stable, what does it mean if it is not stable and still equilibrium?
Something like this, right? Maybe this is V effective versus any coordinate X or R, right? This is stable, this is unstable, this is stable, correct? So I know that if I start anywhere here or there, I will go down the hill to the equilibrium. And if I start close by here, I'll go away from that point because it's unstable, and eventually go down the hill to the stable one. If you start here, you'll go away from this guy, but you are in the region of attraction of this thing, so you'll go here. So it depends if you have multiple, if you have a single equilibrium, and it's stable, then it's globally stable. Start anywhere, you will go to it. But if you have multiple equilibria, then this, for sure, just the fact that you have multiple equilibria, it precludes immediately the ability to have global stability. Okay? You cannot have global stability. Because even if I don't have this one, just the fact that I have multiple equilibria. Why? Because global stability, by definition, says if you start at anywhere, you will eventually go to the equilibrium point. But what about starting right there? This is an equilibrium by itself, which means if you start here, you will remain there indefinitely. So the fact that you have multiple equilibria precludes right away the ability to get global stability. Okay? And if you have multiple equilibria and some of them are stable, so each one will have its region of attraction. Determination of region of attraction is not a trivial thing. It's a branch of science by itself when you take the nonlinear control course. Yes, you.
So you're talking about how like the equilibrium R it will defy gravity, but in physical world it doesn't happen. So how does
No, it happens. I mean, we can build this thing. We have the inverted pendulum case, and actually we broke it in the lab, but we can build this thing. But this has to be frictionless, right?
Oh.
This is our assumption. So indeed, if you have a frictionless table, just pushing some air to make things slide frictionless, what will happen? It will really happen. You just push this, it will come back. It's as if you have a spring. Okay? Yeah.
It will always return.
It will always what?
Return to the stability position.
Yeah.
Always. No matter if the mass is almost on the whole.
Yeah. But you need to give it the sufficient p theta at the beginning, right? So p theta goes with r squared. So if you want to analyze it further, this is indeed r cubed equals m squared r4 theta dot squared initial. This goes away. So if you start at the equilibrium, say, you get that the R equilibrium is g over theta dot naught squared.